Hey guys, Mr. Backerwork here. In this video, we're going to look at Riemann sums. So a Riemann sum is an approximation of a region's area, which can be obtained by adding up the areas of multiple simplified or smaller slices of that region. And a Riemann sum, it's named after the 19th century German mathematician Bernhard Riemann. Now, we've actually already done a type of Riemann sum when we looked at doing our rectangular approximation method, where we took a region, broke it up into these different rectangles, whether it was left endpoint or right endpoint or midpoint. We broke that region up into different rectangles, found the area of each rectangle, and then added those things together. That process is a type of Riemann sum. Now, as we're going through and looking at things, we're going to be using something called sigma notation, and that's going to allow us to express a large sum in a compact form. So this is the Greek letter sigma, and that just stands for a sum. The k value on the bottom tells us where to begin our sum, and the n value on top tells us where to end our sum. Now, this n value could be a specific number, or it could be infinity, which would tell us that the terms go on forever and ever and ever. So what's happening in here, where we have this a sub k going from a k value of 1 up to this specified n value. So this says that we're going to take the first a value plus the second a value plus the third a value all the way out to the nth a value, and we're adding all of those things together. It's a Riemann sum, so we're adding those pieces together. So what we're going to be looking at is a specific function defined on a closed interval from some a value over to some b value. And what we're going to be doing is partitioning up, breaking up this region into different sub-intervals. So we're going to be making different rectangles in here to help us find the area underneath this curve between the curve itself and the x-axis. Now, the thing about these intervals is they don't need to be of equal widths. Some of our rectangles could be wide, some of our rectangles could be narrow, but we're trying to break this up into a whole bunch of different rectangles so that we can find the area of each rectangle and then add all of those areas together using that Riemann sum method to help us calculate what the area underneath this curve is. Now, similar to what we saw before when we were doing our rectangular approximation, the more rectangles that we use, the more accurate our approximation is going to be. So what we're going to be looking at doing in here is along our curve, we'll be finding the height of each one of our rectangles. So if I just pick one of these rectangles to work with, I'm going to look at this one right here on this picture. So I would need to know how tall that rectangle is. So I need to find a point on that rectangle that also lies on the curve. I'm going to call that f of some c value. So f of c represents the height of this specific rectangle. As far as the width in there, that's the change in the x value from the beginning of the interval to the end of the interval. Well, when we're talking about the change in x, I'm going to denote that as delta x. And to find the area of that rectangle, I would multiply this height by that width. So we're going to do that for every single one of these rectangles along this curve. And then we're going to add up all of those individual areas that we just found. So that's where our Riemann sum is coming into play. So we're going to do a sum of a whole bunch of different rectangles in there, which is going to give us our total area underneath that curve. Now, like I mentioned, as we use more and more rectangles, the more accurate our answer is going to be. There's this thing called the norm of the partition. So it's almost like two absolute value bars around this P. That means the norm of the partition. And all of that means the norm of the partition is the longest sub-interval in our picture. So remember, I said not all of the rectangles need to be of equal width. So in this picture, we can see that we've got some really narrow rectangles, and we can see that we've got some wider rectangles. The norm is the length of the longest sub-interval. And what we're going to look at doing is making this norm tend to 0. So that means that we're going to make the biggest rectangle in here get closer and closer to a width of 0. And the more narrow your rectangles are, the more rectangles you're going to be able to fit underneath your curve, and the more accurate your approximation is going to be. So all of that is leading us to this idea of a definite integral. So looking at a definite integral as a limit of Riemann sums, we're going to let f be some function defined on a closed interval from a to b. For any partition p of that interval from a to b, we're going to let the numbers c sub k be chosen arbitrarily in any subinterval along those rectangles that we were looking at. If there exists some number I such that the limit of this sum as that norm heads to 0, so remember the norm is the width of the biggest rectangle, so as your rectangles keep getting more and more narrow, if this sum approaches a specific I value, no matter how that partition p value and how those c sub k's are chosen, then we can say that our function f is integrable on that interval from a to b, and that I value is called the definite integral of f over the interval from a to b. Now, all continuous functions are integrable. So that means if we've got some function f that's continuous on an interval from a to b, then its definite integral over that a to b interval has to exist. Now, because this theorem guarantees that the definite integral of a continuous function has to exist, it actually makes some of the calculations a little bit easier for us. Earlier on, I said as we were creating all of these different rectangles, they didn't have to be of equal width. But because we know that the definite integral is guaranteed if we're dealing with a continuous function, then it makes the most sense for us to choose equal width rectangles along our entire picture. That's going to make doing all of these calculations that much easier. So if we're doing the definite integral of a continuous function on an interval from a to b, we're going to let f be our continuous function on that a to b interval, and we're going to let a to b be partitioned into n subintervals of equal length. And the way we're going to calculate that width is by taking our ending interval value minus our beginning interval value and then dividing it by that n value. And n just stands for the number of rectangles that we want to create. So if we do that, then the definite integral of our function over that interval from a to b is going to be given by the limit as the number of rectangles that we're creating is approaching infinity. So we're creating smaller and smaller rectangles until we can essentially fit an infinite number of rectangles underneath our curve. So then what we're going to do is this Riemann sum of our function using that delta x width for all of those rectangles. Remember, this f of c value represents the height of any individual rectangle, and this delta x represents the width. So we're calculating the area of a whole bunch of rectangles, and then this sigma notation means that we're adding up the area of all of those rectangles together. That's going to be it for this video. Thanks for watching.